All right, guys. So let's start. That's okay with you. Um, First of all, thank you for coming. I tried to make this session like face to face because for the past two lectures, uh, I've been just speaking to my computer screen, and I feel like it would be more productive if we talk with each other like in a real lecture feeling. Um, First, I have to say that the entire uh, time is going to be recorded, and then we're going to post it as the third part of the second lecture. So you guys can go back to it and watch it again if you want, and people who did not come will be able to watch it, of course. Good. So what else? Yeah, in Zoom there is the limitation of 40 minutes. So if it disconnects after 40 minutes, just rejoin the meeting, and then we're gonna pick up where we left off. And hopefully it should not take more than 40 minutes anyway. So good. So last time, so the second part of the previous videos, we stopped at this slide. And we go back to the same questions that we asked before. What exactly is the role of ICT that plays in the management of smart grids? And we define it in these list of questions just to kind of think about the problems that we can solve with ICT. So I would like to get your feedback on this from what you guys saw in the previous slides. So you can unmute now, and let's discuss these questions a little bit. So what do you guys think that we can sense with a remote infrastructure?
I think we can sense wind power or solar power.
Yes, good.
For example.
Maybe something at the user side. So wind power and solar power, this describes the generation side, right? So this can be at the user side also. What about things that are related to the consumption?
Yeah, how much energy is consumed, of course.
Yeah, so we have these smart meters that are being deployed right now over Germany, right? And these are ways to measure the consumption of the user remotely. Right now, it's not very remote, but at least they don't have to go inside the house to measure the usage anymore. So these are examples of things that we can sense. How frequently depends on the value that we're measuring. So for example, how frequent do you think we need to measure the generation, like the solar power, for example?
Maybe every 15 minutes.
Yes, so this is a kind of like a middle value, which is good because you can interpolate the values in the middle. So you can measure every 15 minutes, and then you can kind of draw the interpolation between 2 or 3 points and find the middle values. So that should be enough. But if you're measuring something like the currents running in the power lines, how frequent do you need to measure that?
You mean the clouds?
No, the current in the power lines themselves, in the wires.
Okay. Maybe even more often.
Yeah, it's a lot more often than 50 minutes. So usually that needs to be measured on a millisecond scale because it needs to detect the short circuit faults, and the grid itself needs to react to these kind of faults quickly in order to protect the grid components from fire or failures, right? Good. So now we know that different parts of the grid requires different frequencies of measurements. And the third question that we come to is, what is the area? How big is the area that we need to cover? And it's related to the fourth question, which is, depending on how big the area that we need to cover, we need to choose the telecommunication technology that we can work with, right? So if we talk about a scale of households, then we have maybe 500 meter, 400 meter radius. Even within the wireless, if we choose to work with wireless technologies, then we need to figure out which kind of wireless technology do we use. So Wi-Fi, for example, has limited coverage capabilities. So it can goes up to tens of meters, maybe 100 meters. But if we're talking about 500 meters radius, then we need to find another wireless technology that can give us these capabilities. And this is where different IoT wireless technologies come in play, and we're going to talk more in details about that in the next lecture. But for now, it gives you an idea of how to think about a problem when you're talking about smart grid management. Then, of course, how much data are we dealing with? If we're, of course, data is a quantity per time, right? So if we're talking about measuring every 15 minutes, then it's not a lot of data. But if we're talking about measuring every millisecond, then the amount of data we're transmitting per minute is quite high. And of course, the consequence of failure dictates how fast we should be in detecting that failure. Because if a failure in the network is acceptable or it's not a big deal, then we don't need to react to it that quickly. But if we have, like in the power grid, that short circuit faults can cause fires or destruction of equipment, then we need to be very fast in reacting to these faults. Okay, so this is more or less where we stopped last time, right? And building on this information, we go into the next part, which is this feedback loop of IoT. So basically, the loop starts at the sensor side. So Internet of Things means that it's a connection of different things, and the things themselves are either sensors that measure a certain quantity or actuators that control a certain aspect of the grid. So it starts at the sensor side. So the sensors are measuring a certain quantity. We talked about whether it's generation side or consumption side. Now, these information are being measured and then transmitted through IoT protocols that are mostly wireless nowadays. And these quantities, these measurement quantities, are being transmitted to a gateway. Now, the gateway works as a connecting point between these different sensors, sending different amounts of data to the cloud or the internet. So the gateway's function is to gather this information from many sensors or many different types of information and constructs a packet of data and sends it to the internet. And then in the cloud, in the internet, this information can be processed, and either you can use machine learning algorithms to decide a certain action. So for example, if we measure the generation and the consumption, and we need to tell the electrical equipments at the user side to stop working because the generation is going to decrease. So we need to decrease the consumption as well. So this decision is being constructed at the cloud, so at the internet side, and then sent again through the same channels back to the actuators that control the electrical equipments at the user side. So it's mostly a closed loop. You get information from the network, you process them, you build the decision to control a certain aspect of the network. So it keeps it balanced. So when we detect a decrease in the generation, then we need to tell the consumption to lower down, or when we detect that the consumption is low, then we need to tell the batteries to start storing energy, because we're not going to use that energy right now. All right, so any questions so far? Is this part clear?
No questions, thank you.
Good. So now the part where the information is being transmitted, this can be described by different network topologies. So how these things that we call them are connected together or connected with the gateway can be described by certain topologies. We call them network topologies. There are four main ways that you can interconnect a number of terminals, whether these terminals can be sensors, actuators, computers, or routers. There are four main ways. First is the bus topology. So you have a main, let's call it a medium, wireless medium, and all these different terminals are connected to it. So any information that passes through this medium, this way of transmitting information, will be or can be accessed by all the terminals connected to it. It's also worth to mention that these network topologies are not only for wireless, but it's also for wired. So you can connect different terminals via wires, also using these different network topologies. So the bus topology is useful when you have a subscription-based service. So these terminals will subscribe to this main medium, and then they can access all the information that is being transmitted on it when they want to, or they can also send information to this medium that can be accessed by all other terminals. The next one is the ring topology, and as you can see, the medium is kind of passing through all the terminals, which means that you cannot send information from one terminal to another that is multiple hops away from it without passing through the intermediate terminals. So the distance between a certain terminal and the one adjacent to it is called a hop, one hop, or two hops, or three hops, and this measures the distance between different terminals. This scenario is kind of not optimal when it comes to security-based or security-crucial transmission, because the information passes through different terminals, which means that the information might not be as intended for you, but you have to receive it and retransmit it again. The third topology is the star topology, and it's the normal topology in router-based networks. So when what you have at home, all your terminals are connected to the same router or switch. And if you want to send information from one terminal to another, then you have to first pass through the router that routes your information to the intended destination. The fourth and the last topology is the mesh topology, and this is also called ad hoc networks. And it's basically the interconnection of multiple terminals that construct a network-like environment. And the good thing about that is that if you want to access one terminal then you can choose the route that you want to use. So you can have multiple different routes. You can go, do you see the cursor? Do you see my mouse?
Yes.
Okay.
Yeah.
So you can route it this way, or this way, or this way. This ensures reliability. If one link or one route is not optimal or does not work good enough, then you can have multiple other routes to use. The mesh topology also represents the interconnectivity of the internet itself, and routing algorithms in the internet tries to find the optimal routes through billions of different routes, and there are very efficient algorithms to do that. Good, so now we have spoken about the internet. It's also quite useful to talk about the OSI model of the internet. So the OSI model represents an encapsulated functionality approach to describing the internet. The reason why people follow this model is because you don't want to talk about everything at the same time. So you kind of divide the functionalities into different layers. And therefore, when you're designing a certain protocol, you can put it in one of these 7 layers and kind of talk about a certain part of the functionality. It's going to get clearer as we explain it. So let's start at the top. Let's start at the application layer. So at the application layer, you have the end user layer. So this is the kind of the application that we're using. So whether it's a web browser or a Windows Office application, this is the actual application that you're using. Now, this application, when it needs to access or to communicate with another terminal somewhere else, so let's assume that you want to send an email, right? So the email contains the text that you want to send. Now, this text is handed down from the application layer, which is your email browser, to the presentation layer. And the presentation layer is kind of a representation neutral layer. So it's independent from the way the application describes the data. It translates it from the way the application describes the data to the way the data needs to be in order to be transmitted in the internet. So it's kind of like it's the first interface between your all the applications that you have on your computer that access the internet and the way data needs to be represented in order for it to be transmitted somewhere. So this kind of like has a universal representation of data, and then it connects to a certain application and translates the data in different directions, whether it's from the application to the internet or from the internet to the application. Kind of like the translator in the middle. It also adds certain security or encryption, decryption algorithms, as you can see here, SSL or SSH. Then after the data is being encrypted or decrypted, it's passed through the session layer. Now the session layer is responsible for 2 main things. The first thing is to establish a communication session between 2 different points. This point can be your computer and your router at home. And it also describes the amount of time you will wait before the session times out and automatically closes. It does a second thing, which is the division of, the division of data is being done in the transport layer, so we'll get to that. So as we said, the session just establishes the different sessions between, the different sessions of communication between 2 different points. Now we come to the transport layer. And the transport layer describes end-to-end communications or end-to-end connections. So it describes the port number that you want to access. So at each point in the internet, whether it's your computer, your router at home, a router at a different network at work, for example, there two different things describing the address. There's an IP address that is established first at the network layer, and then there's a gate number that describes at this IP address which gate should we use. And the transport layer describes this gate number that we are required to use. It also divides the data that you want to transmit into segments. Now, these segments are passed to the network layer, and the network layer builds packets based on these segments of data. So it takes a segment of data and a port number, builds this packet, and adds on top of it the IP address, which is like the building address. And then you need an apartment address to know exactly who are you going to send this data to. And the apartment address is the port number. You can kind of like get the analogy. So after the packet is built and assigned a certain IP address, it passes through to the data link layer. And in the data link layer, these packets and IP addresses are put into frames and ensures that there are certain ways to correct errors that happen during transmission. So whether this is a CRC or parity check or something that is added to the original data in order for errors to be corrected at the destination side. Then after this frame is being built, it passes to the physical layer, which mainly describes the actual transmission of the data in raw bits, so in binary. And the physical layer can be wired, so it can be coaxial cables, fiber optics, or it can be wireless in the form of your Wi-Fi at home, or a certain repeater that just receives the signal and retransmits it again. You're not supposed to know exactly the functionality of each single layer of the model, but you should be kind of familiar with how the data goes from the application all the way to the transmission phase. Right. Good. So any questions here? Okay.
No.
Good. So next is, so this tells us kind of let's call it how a certain application at your home computer communicates with an application at a certain data storage or a certain database facility, or you can call it also the internet. And in order for a certain application to communicate with a certain application at another location, it has to go through all the layers first at your terminal and then transmit it. And then you have in the middle here these repeaters or hubs. And at every single hub, you have only these first three layers, because at the data link layer and at the data link layer first, errors are being corrected. And then at the network layer, the IP of the next hub is being allocated. So first your terminal connects to a hub. So this is the physical layer transmitting the information. Then it's received at a certain hub. Then it goes up to the data link layer. The errors in the received signal is being corrected. Then it goes to the network layer where the IP of the next hub is being assigned. Then it goes down again, transmitted, same thing. And then the IP address here of the final destination is being assigned and then transmitted, and so on. So this is the operation of two applications communicating with each other through the internet. And in this example, you only have two hubs, but in a normal internet access kind of scenario, you will have more hubs than that. Of course, depends on where. So if you're communicating with an application that is placed in the US, then you will have much more hubs in the middle. But if you're communicating with an application that is on your own Wi-Fi network at home, then you will only probably have one hub, which is your router, your home router. Good. So far, do you guys have questions?
No.
Good. Okay. So what about IoT? Is the Internet of Things follow the same representation or the same modeling of communication? Now, to a certain extent, yes. But there are differences between the two models. And the reason for that is because these chips, these sensors, or these actuators, they don't have real applications that need to be communicating with the different applications. So it does not need the whole capabilities and functionalities of the 7 layers of the OSI model. And therefore, these sensors, they kind of have only the 4, so these are the 3 layers: session, network, and data link. And you have down here is the physical layer also. So the reason for that is because, as we said, for these off-the-shelf sensors or actuators, you don't have an actual application that needs to be translated into the presentation layer and so on. You just need a session layer to establish a communication session between the sensor node and the gateway, and to kind of describe the form of communication that they will be sharing. Then you need the network layer to establish the address of the destination that you want to reach, and to kind of perform the routing, whether you're going to do from one sensor node to one sensor node, or you're going to do the transmission from one sensor node to the gateway. And you also need the data link layer to ensure that there is error correction capabilities at these packets. And of course, you have the physical layer that handles the actual transmission of information. Now, the gateway, any Internet of Things network, performs as an interface between these sensor nodes that have a different representation of communication than the internet itself. So here you see that at one side you have the sensor nodes that have this representation of communication, and then they communicate with the gateway, and then the gateway has 2 sides. First, the side is the side that is facing the sensor nodes, works the same way as the sensor node works, so it kind of receives the information and then goes from the bottom up. It goes through data link layer, network layer, and then session layer. It reaches the information that the sensor is transmitting, whether it's a reading of current measurements at the power lines or reading of generation in solar panels, and then goes through the main the OSI model again from the top to bottom in order to send it to the internet. So from one side, it has a representation of communication that passes to the way the sensors are built. And from the other side, it has a representation of communication that passes to the way the internet is built. And this is why a gateway in IoT networks is very important. And usually you cannot use a normal router that you have at home. You need a specific gateway that has this representation at one side and this representation at the other side to work as an interface. Is this more or less clear?
Yeah. So the gateway is this second thing here. right?
So the internet way is the part on the right side, and the IoT communication model is the one on the left side, right? And the gateway of an IoT network works as an interface in the middle between these two different representations. It's kind of a translator. It gathers the information from the different nodes and translates it into the way the internet works.
Ah, okay, yeah.
Yeah. Okay, so this is clear now. Good. So we'll take a pause here. So there's only one part next left, but I don't want the session to stop in the middle. So I don't know how much time have we been doing so far.